So it's time to deep dive into the probability theory. This will be our first lesson where we will be defining the various models for finding a probability, right? So we will subdivide our probability theory sessions into two kind of models. The first one will be your classical model of probability, and the second one will be state theory model of probability. Please note whatever we have learned so far in our prerequisite or in counting will be heavily used in the probability, right? So the probability will simply use the concept which we have learned so far. So there is nothing new into this apart from few instances which we will be studying in depth. So let's see what is a classical model. Okay, so we will start with the classical model of probability. So in order to understand the classical model of probability, or in order to understand probability, first we have to define few of the things which are called random events, right? So what is a random event? The first thing which comes to mind is event, because in probability you will see that this particular word event is quite used, and so we need to understand this event. So the any event or a random event is something whose outcome is not known, right? So for example, if you flip a coin, you don't know whether head will come or tail will come, right? So this is an event, right? Flipping a coin is an event where you don't know the outcome. So these kinds of events where you don't know the outcome are called the random events, right? So I'll give you few more examples of random events so that you understand it. Random events, okay, where the outcome of the event or the outcome of experiment is not known. So similarly, if you roll a dice, right? So you actually don't know whether 1 will appear on the front face, 2 will appear, 3 will 4, 5 or 6 will appear, right? So these are the random events. This event of rolling a dice and getting some number is an event, and which is random in nature. So the idea of probability is to estimate the randomness of those events. So for example, if you flip a coin, what is the probability or how you are going to estimate that how many heads will come and how many tails will come? So the one approach of doing that would be that you roll that flip a coin, let's say 10,000 times, and write how many times the head will come and how many times the tail will come. And similarly, we'll say that okay, out of 10,000 times, 5,000 one times head has come and 4,999 times the tail has come, right? So this is head and this is tail. So by probability we estimate that the probability of getting head will be nothing but 5,000 by 10,000. We will see how the classical model will come into picture, and probability of tail is approximately, because as you increase or decrease the number of tosses, it might be possible that these numbers may vary. But for the sake of clarity, in our classical model, we define few more terms. The first one is mutually exclusive events. Okay. Then we define exhaustive events. And finally we defined equipossible events. So these are the few terms which we will be requiring for the classical model of probability. So let's see what all these terms means. So we will just explain that using this. Okay, so now suppose we are carrying out an experiment which has the number of possible outcomes. So like for when you toss a coin, the outcomes could be head and tail. And when you roll a dice, it could be 1, 2, 3, 4, 5, 6, which is coming on the top, right? So let A1, A2, and AN are all, and we defined A1, A2, A1. Okay, so we say that A1, A2 are called mutually exclusive if they exclude each other, that is among them there are no common events that can occur simultaneously. So it clearly means that all these events are different, right? So for example, when you wrote again flip a toss a coin, then you either get head or tail. So if an event A1 in this case of tossing a coin, if the event A1 is getting head and A2 is getting tail, right? So at the same time, when you flip a coin, you can't get head and tail both, right? So they are mutually exclusive. It cannot happen simultaneously. These two events cannot happen together, right? So they are called mutually exclusive if they cannot happen together, right? Then we say that event. Okay, so we call it there's something called exhaustive. So we say that event at A1, A2 all are called exhaustive if they cover all possible outcomes. That is it is impossible that none of them occurred as a result of the experiment. So again, if you look at here, so A1 is getting head on a flip of a coin, A2 is getting tail on the toss of a coin, right? So if you add these two, you will finally exhaust all the options because either you will get head or tail. So the total number of outcomes which can come from tossing a coin is either getting a head or getting a tail. Let's take few more example of, so when we roll a dice, so we define B1 as getting 1, B2 as getting 2, B3 as getting 3, similarly B4 as getting 4 on the top of it, getting 4, and B5 is 5 and similarly getting 6, right? So these are mutually exclusive because 1 and 2 cannot come together, right? It will be either 1 or 2. Now these are the only possible values, possible outcomes of an event when you roll a dice. So this is completely exhaustive events. This set of events are exhaustive. Similarly, we write the third condition as that. Okay, so here is the third condition. Okay, so this is our third condition. So if A1, A2, A3 and A4 are equally likely, meaning by that all the events could occur in a equal way, then this is called, all the events are called equally likely, right? So if all these three conditions are fulfilled for any set of events, then we can use the classical model, right? And we call that probability as a chances. Okay, so if you take a look at the example of equally likely, so if a coin is fair, then the probability of the likelihood of getting head and tail are same. Similarly, likelihood of getting 1, likelihood of getting 2, likelihood of getting 3, likelihood of getting 4, likelihood of getting 5, or likelihood of getting 6, all are same, right? So in this case, in both the cases, we have seen that they are mutually exclusive, they are exhaustive, and they are equally likely, right? Now let's take some of the examples and let's try to answer this question when they are equally likely, exhaustive, or mutually exclusive. So for example, okay, now let's take this set of events. We will just increase the font of it. Okay. Consider now the experiment consisting in tossing 2 coins. Okay, and we try to enumerate all the possible outcomes. The 3 events here noted are B1 is, so when you toss the 2 coins, so let's say you toss the 2 coins together. So you take in 2 of your hands and toss all those coins. So what are the possible outcomes which you can get? So we define B1, B2 and B3 as appearances of two heads. So it is possible that both the heads will appear together. Then there is a possibility appearance of two tails. Then it says the appearance of one head and one tail, right? One head, one tail, or so in this case also the first coin will get tail and the second coin will get head, right? These are the, so if we look at it, these are mutually exclusive because appearance of two head and two tails cannot happen together. Appearance of head tail, appearance of head cannot happen together. Appearance of tail head and tail cannot happen together. So these are basically your mutually exclusive. So we write it as ME. Now let's try to find whether they are exhaustive. So exhaustive is all are, these are the only four possible outcomes because so this set, so this is our B1, this is our B2 and this is our B3, right? So you will see that okay, apart from B1, B2, B3 there is no way you will get the outcome. So these are completely exhaustive, right? Now if you look at what are the probabilities or possibilities of getting this, so you can see that head and head is 1, tail and 2. So if you find the probability, it seems like clearly it seems like this is not possible because B3 can happen in 2 ways out of the 4, B2 can happen in 1 way out of the 4 and B1 can happen 1 way out of the 4. So these are not equally possible, not equally possible. Okay, so here we cannot use the condition our classical model, right? Similarly, if you look at another example so that you get more and more clarity of it. Okay, so now let's try to solve this. Okay, so it says that two paired dice are tossed. Let X be the event that the first dice throws an even number. When two dice are tossed, okay, so what are the possible outcomes? The possible outcomes are, the first dice is getting 1, second dice gets 1, the first dice gets 1 and second dice gets 2, and similarly all the possibilities, right? So we say that the event that the first dice throws an even number. So the first dice always appear with 2, 4 or 6, right? And second dice is with the odd number 1, 3, 5. So these are the numbers which appear on the various dice. Now, are they mutually exclusive is the question. So is it possible that when these two events cannot happen together? But if you look closely, that these two events can happen together, that in such a way that if you roll a 2 dice, then the outcome is 2, 3, which is on the first dice, D1, and this is G2. So they can happen together, right? So they are not mutually exclusive. Are they exhaustive? So, if you find all the possible combinations and you try to find all the possible combinations from here, you will see that it is not exhaustive. So they are not they are not exhaustive. But since we have, are they equivalently? Yeah, because there are three possibilities which are there, and there are three possibilities here. So these are equally likely, right? So these are equally likely, but they are not mutually exclusive and they are not exhaustive, but equally likely, right? So again, in this case, we will not be able to apply the classical model. So in the classical model, we will not be able to apply the classical model. In the next session, we will see how the probability is computed using the classical model. If you want to see more such videos, do subscribe to our channel or visit our website deepdivemaths.com. Thank you.